on state. So if a negative voltage is applied to emitter, immediately the PN junction diode become reverse biased, the emitter current becomes zero, and the device is said to be in off state. So if you want to turn off the device, I have to give negative voltage to the emitter. If I want to turn on the device, I have to give positive voltage to the emitter. Okay, I have to give positive voltage to the emitter. So any doubts in this operation of UJT so far? If you have, you ask. I'm going to pause for a few minutes. So now we are going to see the characteristics of UJT. So now we are going to see what is the VE versus IE characteristics. So if I'm going to vary the emitter voltage and what is the effect on the current. Okay, so I'm going to take IE along x-axis and VE along the y-axis. So up to peak point P, the diode is reverse biased. So you can see that when you are going to increase the voltage till a particular point, the diode becomes reverse biased. You know that until V becomes greater than V1, the diode is reverse biased and it will not conduct. Correct. So until the peak point VP, the diode is reverse biased and it will not conduct. So that region you see it is marked as cutoff region. Cutoff means the diode is in off state. So once you are going to give a positive voltage to the emitter, at that point when I'm going to give a firing voltage VP, which depends on the parameter, that firing voltage is given to the emitter. So this is the emitter voltage what you have. The diode starts conducting. So once your voltage in the emitter crosses V1, the diode is forward biased and start conducting. Hence the resistance decreases, and because heavy current is flowing, so the resistance will decrease, thereby decreasing the VE for increase in IE. See the diagram. So after the peak point, the device becomes forward biased and heavy current is going to flow through the device. You can see the current is increasing, voltage is decreasing because resistance is decreasing, but the current is still increasing. You can see the current is increasing from IP to IV, and the current reaches a minimum point called valley point. The voltage reaches a minimum point called valley point. So you see there in the diagram, current is always increasing in this diode. Only thing, the voltage is reducing after the peak point because there is negative resistance. What is negative resistance? When you are increasing the voltage, the current will decrease. That is negative resistance. But here, when I'm increasing the current, the voltage is decreasing. It may happen in either ways. Either voltage is increasing and current is decreasing, or voltage is decreasing or current is increasing. It can be either ways. But here you see my voltage is decreasing, but the current is increasing. So there is a negative resistance region from the peak point to the valley point. After the valley point, you know, enormous amount of current is flowing into the device, so the device will be in saturation and it behaves like conventional PN junction diode. It behaves like conventional PN junction diode. So to the right of the valley, we have what is called as the saturation region. So in this valley point, the resistance changes from negative to positive. Only after the valley point, it again starts increasing. At this point, when as voltage is going to increase, the current is also going to increase. In that point, you can say that the resistance would also become positive. So the resistance remains positive in saturation region, and the resistance remains negative in negative resistance region. For very large value of IE, the curve reaches the approaches the curve for IB2 equal to 0. So it approaches the conventional BN junction behavior for large values of VE after the valley point. So this is going to be the forward bias characteristics of your UJT. So any query if you have, you can ask in this graph. So I'll just quickly explain the graph once again. Please understand it clearly if you have not understood it now. So initially, when the voltage is very less, till a particular peak point, if you increase the voltage, the diode will not, the UJT will not conduct, so the current will be very, very minimum. That is till the peak point, VP and IP. So once, even after you increase the peak point, after increasing the peak point, what happens? The diode becomes forward biased and heavy current will flow through your device. So current will increase, but that will, when a heavy current is going to flow, the resistance is going to be zero. So the voltage will start reducing till a point, valley point. At the valley point, the device is already having heavy current, it is into saturation. So even how much ever you increase after the such valley point, the current will be increasing proportionally and it will follow the conventional PN junction behavior. And when you are going to have negative values of your VE, you are going to have the leakage current flowing to the device. So we have studied, right, when the emitter junction is reverse bias, then you will have, ideally you will have zero current, but practically you will have a very small reverse saturation current flowing to the device because of minority carriers. So that is the leakage current which is mentioned in the graph. So three regions we have. Cutoff region is where the device is off. Negative resistance region where the resistance is reducing, and saturation region where the current is very high. So cutoff region is where the device is said to be in off, and saturation region is where the device is said to be in on state. The negative resistance region provides the transition from the off state to the on state. Okay, so that is in UJT, two things you have to explain. One is the operation of the circuit of the device, and second thing is the graph. This graph is very, very, very important in the case of UJT because this is the second device we are seeing which has negative resistance region. What was the first device we studied which had negative resistance region? Yesterday we have seen one device, right? Can anybody remember that? Yesterday we have seen one device having negative resistance region. What is that device? Anybody remembers the name of the device which had negative resistance region yesterday? No? It is tunnel diode. Tunnel diode also has negative resistance region. This UJT is also going to have negative resistance region. So one unique feature of UJT is unless the emitter current is properly given, UJT will not be triggered. So unless you supply the necessary amount of emitter current to the device, the UJT will remain off state only. Only when you give a proper negative resistance to the proper triggering voltage to the device will turn on from the off state to the negative resistance region. So due to negative resistance property, UJT can be employed in lot of applications shown here. I told you one point yesterday, all devices having negative resistance property can be used as oscillators. So all devices having negative resistance property can be used as oscillators. So UJT can also be used in oscillator. See here, sawtooth wave generator, pulse generator, switching, timing and phase control circuit. So mainly it is used in waveform generation and oscillator